March 15, 1943. A snow-covered field 8 miles southeast of Bremen, Germany. Oberleutnant Klaus Richter knelt beside the wreckage of an American B-17 Flying Fortress, his gloved hands carefully extracting a metal device from the shattered nose section. The bomber had gone down during a daylight raid just hours earlier, its crew either dead or captured. But Richter wasn't interested in prisoners. He was staring at what Luftwaffe intelligence had been desperately seeking for nearly 2 years, an intact Norden bombsight. The device was surprisingly compact, roughly the size of a large typewriter, weighing perhaps 50 pounds. Its outer casing was dented from the impact, but the internal mechanisms appeared undamaged. Through the broken housing, Richter could see gears, gyroscopes, and optical elements machined to tolerances he had never encountered in German equipment. This was the device that enabled American bombers to drop their payloads from 25,000 feet and hit targets the size of a factory building. This was the secret weapon that Luftwaffe analysts believed was impossible to build with existing technology. As Richter supervised the careful extraction and transport of the bombsight to the nearest Luftwaffe technical facility, he understood he was looking at something that would fundamentally challenge German assumptions about what American industry could produce. Within days, the device would be in Berlin, where Germany's most skilled engineers would begin a systematic examination that would lead them to a single devastating conclusion. They had been fighting an enemy whose technological sophistication and manufacturing precision exceeded anything Germany could match. The story of how German engineers came to examine, fear, and ultimately despair over the Norden bombsight began not in the wreckage of bombers over Germany, but in the laboratories and workshops of the United States, where, in the early 1930s, a brilliant but difficult engineer named Carl Norden was perfecting a device that would revolutionize aerial bombardment. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Carl Lucas Norden was born in Java in 1880, the son of Dutch parents. He studied engineering in Switzerland, receiving his diploma from the Federal Polytechnic School in Zurich in 1904. After immigrating to the United States in 1904, he worked for various engineering firms before joining the Sperry Gyroscope Company in 1911. At Sperry, Norden worked on gyroscopic stabilization systems for ships and aircraft. His expertise in precision mechanics and gyroscopic instruments caught the attention of the United States Navy, which was struggling with the fundamental problem of aerial bombardment. Dropping bombs from moving aircraft onto stationary targets presented mathematical and mechanical challenges that seemed almost insurmountable with 1920s technology. An aircraft flying at 200 miles per hour at an altitude of 10,000 feet had to release its bombs several thousand feet before reaching the target. The bombs would continue moving forward at the aircraft's speed while simultaneously falling due to gravity. Wind affected the bomb's trajectory. Air density at altitude changed ballistic calculations. The aircraft's speed and altitude had to be measured precisely. In 1923, Norden left Sperry and established his own company, Carl L. Norden Incorporated, specifically to develop a precision bombsight for the United States Navy. He partnered with Theodore Barth, a former colleague from Sperry who brought crucial expertise in optical systems and mechanical engineering. Together, they began work on what would become the most sophisticated piece of precision equipment deployed during World War II, the Mark 15 Norden bombsight. The version that would see extensive combat use represented more than a decade of continuous refinement. The device combined 3 fundamental systems: a stabilized sighting head, an analog mechanical computer, and an autopilot interface. The sighting head used a complex arrangement of mirrors and lenses that allowed the bombardier to track a target despite the aircraft's motion. A gyroscope, spinning at approximately 7,200 revolutions per minute, provided a stabilized reference platform. This gyroscope had to maintain perfect stability despite the aircraft's turbulence, changes in direction, and the vibration from 4 massive radial engines. The mechanical computer was perhaps the most remarkable component. Using gears, cams, and differentials, it continuously calculated the bomb's trajectory based on multiple variables: aircraft altitude measured by a sensitive altimeter, Aircraft speed measured by airspeed indicators, wind speed and direction entered manually by the bombardier, and the ballistic characteristics of the specific bombs being carried. These calculations were performed mechanically, with rotating shafts and precisely machined gears computing the mathematical relationships in real time. The accuracy depended entirely on the precision of the machining. Gears had to mesh with tolerances measured in 10,000ths of an inch. Bearings had to spin with virtually no friction or play. Optical elements had to be ground and polished to specifications that challenged the capabilities of even the finest optical workshops. The bombsight connected directly to the aircraft's autopilot during the final bombing run. The bombardier, looking through the sight and tracking the target, would make small adjustments to align the crosshairs. These adjustments fed directly to the autopilot, which made corresponding corrections to the aircraft's heading. The pilot relinquished control during these critical minutes. The bombardier and the Norden sight flew the aircraft. When the mechanical computer determined the precise release point, an electrical signal triggered the bomb release mechanism. The entire sequence required extraordinary coordination between human skill and mechanical precision. Development and testing continued throughout the 1930s. The Navy funded the work, recognizing that precision bombing could transform naval warfare. Army Air Corps observers witnessed demonstrations and quickly realized the device's potential for strategic bombing. By 1938, the Norden bombsight was achieving remarkable accuracy during test drops. Under ideal conditions, skilled bombardiers were placing practice bombs within 100 feet of the target from altitudes above 20,000 feet. This represented accuracy improvements of several orders of magnitude compared to earlier bombing methods. The military services recognized they possessed a potential war-winning technology. Security became paramount. The Norden bombsight was classified at the highest levels. Guards accompanied every movement of the devices. Bombardiers took oaths never to discuss the site's operation. During training flights, the bombsight was installed just before takeoff and removed immediately after landing, stored in locked vaults between uses. Bombardiers were instructed that if their aircraft was in danger of being captured, they were to destroy the bombsight by any means necessary, including using a hammer stored in the bombardier's compartment specifically for this purpose, or if time permitted, thermite grenades that would melt the device into slag. The paranoia was justified. If enemy forces captured an intact Norden sight and understood its principles, they could develop similar devices. German bombers with precision bombsights could devastate British industry. Japanese bombers could accurately strike American naval facilities. The Norden sight represented a crucial technological advantage that had to be protected at all costs. Production began ramping up as war approached. The Norden Company's facility in New York could not produce bombsights in the quantities the military services demanded. Additional manufacturers were brought into the program. Remington Rand, known for producing typewriters, began manufacturing Norden sights under license. Their expertise in precision mechanical assemblies made them ideal for producing the complex mechanisms. By 1941, multiple facilities were producing Norden sights. Production standards were extraordinarily stringent. Every component was inspected multiple times. Assembled bombsights underwent extensive testing before acceptance. Rejection rates for out-of-tolerance parts ran as high as 30% in some production runs. The military accepted these costs because even small deviations from specifications could compromise accuracy. When America entered World War II in December 1941, the Norden bombsight was already in production and equipping heavy bomber groups. The B-17 Flying Fortress and the B-24 Liberator, America's primary heavy bombers, were designed from the outset with accommodations for the Norden sight. The bombardier's position in the aircraft's nose provided clear forward visibility essential for the sight's operation. Strategic bombing doctrine developed by the Army Air Corps assumed that formations of heavy bombers flying at high altitude beyond the effective range of most anti-aircraft fire could destroy specific industrial targets with precision. The entire doctrine rested on one assumption, that the Norden bombsight would enable that precision under combat conditions. Early combat operations suggested the doctrine was sound. In August 1942, the 8th Air Force conducted its first heavy bomber mission against targets in occupied France. B-17 seconds attacked the marshalling yards at Rouen from 23,000 feet. Bomb pattern analysis showed reasonable accuracy. Similar missions against targets in France and the Low Countries through late Bomb 1942 produced acceptable results, though accuracy fell short of the extraordinary performance achieved during peacetime testing. Combat introduced variables that test ranges had not replicated. German fighter attacks forced evasive maneuvering that disrupted the stabilized bombing runs. Intense anti-aircraft fire created turbulence and forced aircraft to take evasive action. Weather over northern Europe frequently obscured targets. Bomber crews were young and relatively inexperienced compared to the test bombardiers who had demonstrated the site during peacetime trials. Nevertheless, the Norden site performed well enough to validate the strategic bombing doctrine. Missions continued to expand in scope and ambition. By early 1943, 8th Air Force was conducting deep penetration raids into Germany itself. These missions brought American bombers within range of the Luftwaffe's most experienced fighter units and the densest concentrations of anti-aircraft guns in the world. The loss rates began to climb. The mission to Bremen on March 15, 1943, saw multiple B-17 seconds shot down. German fighter pilots had learned to attack head-on, where the B-17's defensive armament was weakest. Anti-aircraft fire had become brutally accurate, with German gun crews using proximity-fused shells and radar-directed fire control. Among the bombers lost was a B-17F from the 303rd Bomb Group. The aircraft, hit by anti-aircraft fire over the target, struggled back toward the coast but crashed in a field southeast of Bremen. The crew bailed out, and most survived to become prisoners of war. The aircraft, though badly damaged, remained relatively intact. Local Luftwaffe units quickly secured the wreckage. Within hours, technical specialists arrived from the nearest air district headquarters. Their priority was clear: locate and secure the bombsight. This particular recovery would prove significant because the bombsight had survived the crash with minimal damage. The bombardier had not had time to destroy it before bailing out. The thermite grenades remained unused. The hammers stored for emergency destruction had not been needed because the crew escaped successfully. For the first time, German engineers would have access to a nearly intact Norden bombsight. Previous captures had yielded only fragments or devices damaged beyond useful analysis. The device was transported under armed guard to Berlin, to the technical intelligence facilities operated jointly by the Luftwaffe and the Reich Air Ministry. Germany's most experienced engineers in precision optics, mechanical computing, and gyroscopic systems were assembled to conduct a comprehensive examination. The team included specialists from Carl Zeiss, Germany's premier optical manufacturer, engineers from Siemens who understood complex mechanical systems, and Luftwaffe technical officers, with expertise in bomb sights and fire control equipment. Their assignment was straightforward: determine how the device worked, assess whether German industry could produce something similar, and recommend countermeasures. What they discovered would challenge everything they understood about American industrial capabilities. The examination began with careful documentation. Every external dimension was measured and recorded. Photographs captured every angle. The device was weighed precisely. Only after complete external documentation did engineers begin the delicate process of disassembly. They proceeded slowly, removing one component at a time, documenting each step. The outer casing came away to reveal the complex mechanism inside. What immediately struck the German engineers was the precision of the machining. Every gear, every shaft, every bearing showed tolerances that pushed the limits of what German precision manufacturing could achieve. The gears meshing in the mechanical computer had been cut on machines capable of accuracy measured in millionths of an inch. The gears' teeth showed no visible imperfections under magnification. The gyroscope assembly particularly impressed the examining engineers. The rotor spun on bearings that exhibited virtually no friction or wobble. The gimbal system that allowed the gyroscope to maintain its orientation regardless of aircraft motion used jeweled bearings similar to those in high-grade watches. Each bearing's surface had been polished to a mirror finish. The optical system proved equally sophisticated. The objective lens was a compound element, multiple pieces of glass with different optical properties bonded together to eliminate chromatic aberration. The Germans recognized this as a design similar to what Carl Zeiss would produce for premium optical instruments, equipment that cost fortunes and required months to manufacture. Yet here it was, installed in a device that was apparently being produced by the thousands for installation in American bombers. The mirror system that allowed the bombardier to track targets through the aircraft's motion employed first surface mirrors, where the reflective coating was applied to the front rather than the back of the glass. This was necessary to avoid the double reflection that occurred with conventional mirrors, but it made the mirrors extremely delicate and difficult to manufacture. The examination revealed that every mirror was precisely aligned and secured with adjustments measured in thousandths of a degree. As the engineers disassembled the mechanical computer section, they found themselves looking at one of the most complex analog calculating machines ever built. More than 2,000 precision parts worked together to solve the differential equations governing bomb trajectories. Cams, shaped to specific mathematical curves, rotated against followers that translated the cam profiles into linear motion. Differential gears combined multiple inputs to produce outputs representing the solution to complex equations. Every component had to be manufactured too, specifications that German engineers recognized as extraordinarily difficult to achieve in mass production. One engineer, whose name was recorded in the technical report filed with the Reich Air Ministry, noted that the mechanical computer alone represented machine tool work equivalent to what Germany might accomplish in producing 10 aircraft engines. Yet the Americans were apparently installing these devices in every heavy bomber. The implications were staggering. By late March 1943, the technical team had completed their initial examination and prepared a preliminary report. The report, classified as secret and distributed to only the highest levels of Luftwaffe Command and the Reich Air Ministry, included several key findings. First, the Norden bombsight represented a level of precision manufacturing that Germany had achieved only in laboratory instruments and prototype equipment. Producing such a device in quantity required machine tools, quality control systems, and manufacturing processes that exceeded Germany's current capabilities. Second, the bombsight's design assumed unlimited resources. There was no evidence of cost-saving measures or simplified manufacturing approaches. Every component was built to the highest possible standard. This suggested that American industry was not constrained by the resource limitations that German engineers faced continuously. Third, the device's complexity meant that even with complete documentation, Germany could not replicate it within any time frame relevant to the war. The specialized machine tools needed to produce the components would take years to design and build. Training workers to the required skill levels would take additional time. Establishing the necessary quality control and inspection systems would require reorganizing substantial portions of German manufacturing. Fourth, and perhaps most disturbing, the Norden site was apparently just one example of American manufacturing sophistication. If the Americans could produce these complex devices by the thousands, what else were they producing that Germany had not yet encountered? The report concluded with a recommendation that proved devastating in its honesty. Germany should not attempt to copy the Norden bombsight. The resources required would be better spent on other programs with more immediate impact. Instead, Germany should focus on countermeasures, improved fighter tactics, better anti-aircraft guns, and electronic warfare systems that might disrupt the bombsight's operation. The recommendation implicitly acknowledged that Germany had already lost the manufacturing war. The engineers examining the Norden site understood that American industry could produce sophisticated equipment in quantities Germany could not match. This single device, extracted from a crashed bomber in a snow-covered field, revealed a truth that propaganda could not conceal. America's industrial capacity exceeded Germany's by margins that made ultimate defeat inevitable. The examination of the Norden bombsight continued through spring and summer 1943. Additional crashed B-17 seconds and B-24 seconds provided more examples for study. Each captured site underwent similar detailed analysis. The engineers hoped to find variations in quality or construction that might indicate manufacturing problems. What they found instead was remarkable consistency. Every Norden site examined showed identical construction methods, identical component specifications, and identical quality. This was mass production at a level of precision that German industry had never achieved. The devices were not being hand-built by master craftsmen. They were being manufactured on production lines using automated processes and precision tooling. German industry excelled at producing complex equipment in small quantities. Skilled German craftsmen could build extraordinary machines when time and resources permitted. But German manufacturing had not solved the problem of producing precision equipment rapidly in large quantities. The Norden site proved that American industry had solved exactly that problem. Carl Zeiss engineers who examined the optical components reported that the lenses and mirrors matched or exceeded Zeiss quality standards. Yet Zeiss required months to produce a single high-quality telescope or rangefinder. The Americans were apparently producing equivalent optical components by the tens of thousands. Siemens engineers examining the electrical components and mechanical assemblies reached similar conclusions. The quality was equivalent to Siemens precision instruments, but the scale of production was incomprehensible. By summer 1943, production of American heavy bombers was accelerating. Intelligence reports indicated that factories in Seattle, Long Beach, and multiple other locations were producing B-17 seconds and B-24 seconds at rates exceeding 30 aircraft per day. Each aircraft required a Norden bombsight. Therefore, American factories were producing more than 30 Norden sights daily. The numbers defied German understanding of what was possible in precision manufacturing. German bombsight production, by comparison, struggled to meet demand for a few dozen sights per month for the small numbers of German bombers still being produced. The Luftwaffe's primary bombsight, the Luftwaffe 7, was a capable device, certainly adequate for German bombing operations. But it was far simpler than the Norden, used fewer precision components, and required less sophisticated manufacturing. Even with these simplifications, German factories could barely meet demand. The Norden site examination had revealed something far more important than the technical details of one bombsight. It had revealed the fundamental disparity in industrial organization between Germany and the United States. German industry remained organized around skilled craftsmen, producing complex equipment in limited quantities. American industry had evolved toward automated precision production, capable of manufacturing sophisticated equipment at scales that seemed impossible to German engineers. This realization spread beyond the small group of engineers who had examined the captured bombsights. Technical reports circulated through Luftwaffe command and Reich ministry channels. Senior officers who read the reports understood the implications, even if they could not fully grasp the technical details. Germany was fighting an enemy who could produce war material in quantities that would eventually overwhelm German defenses through sheer numerical superiority. The propaganda that depicted Americans as technically inferior, as industrial but not innovative, as wealthy but not sophisticated, was clearly false. The Norden bombsight proved that American engineers and American workers could produce equipment that matched or exceeded the best German precision manufacturing, and they could do it at scale. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Throughout late 1943 and into 1944, the strategic bombing campaign against Germany intensified. The 8th Air Force and the Royal Air Force Bomber Command systematically attacked German industrial targets. American daylight precision bombing using Norden-equipped bombers complemented British nighttime area bombing. German cities, factories and transportation networks suffered devastating damage. The Luftwaffe fought back desperately. Fighter units, despite heavy losses, continued to intercept American bomber formations. Anti-aircraft artillery, organized into concentrated defensive belts around critical targets, downed hundreds of American aircraft. Yet the bombers kept coming. For every B-17 shot down, American factories produced replacements. For every lost Norden bombsight, production lines manufactured more. German intelligence tracked American bomber production based on serial numbers observed on crashed aircraft. The numbers confirmed what the examination of the Norden site had suggested. American industrial output exceeded German capabilities by factors of 5 or 10 in most categories. In precision equipment like the Norden site, the disparity was even greater. By early 1944, some German officers were privately acknowledging that the war was unwinnable. The evidence was visible in the skies over Germany every day. Formations of American bombers, numbering in the hundreds, attacking targets across Germany with apparent impunity. Each bomber represented thousands of pounds of precision aluminum, 4 massive radial engines, sophisticated electrical and hydraulic systems, defensive armament, and a Norden bombsight. The sheer quantity of resources embodied in each aircraft staggered the imagination. That America could produce such aircraft by the dozens daily indicated an industrial base that dwarfed Germany's. The Norden bombsight had become, in the minds of thoughtful German engineers and officers, a symbol of this disparity. It represented not just American technical skill, which Germans could respect, but American industrial organization and resource availability, which Germans could not match. In the final year of the war, as Germany's industrial capacity collapsed under relentless bombing and the resource shortages became critical, captured American equipment told an increasingly desperate story. Every captured Norden site examination confirmed the same conclusions. America could produce sophisticated precision equipment in unlimited quantities. Germany could not. German attempts to develop countermeasures proved largely ineffective. Electronic jamming systems designed to disrupt the bombsight's gyroscopes were deployed around critical targets, but their effectiveness was limited. The gyroscopes used in the Norden site were sufficiently robust that external magnetic or electrical fields had minimal impact. Fighter tactics evolved to attack bombers during their bombing runs when the aircraft flew straight and level under the bombardier's control. But American fighter escorts, equipped with drop tanks that extended their range deep into Germany, made such attacks increasingly suicidal for Luftwaffe pilots. The introduction of long-range P-51 Mustang fighters in early 1944 fundamentally changed the equation. German fighters that attempted to intercept bomber formations now faced skilled American fighter pilots, flying aircraft with performance equal or superior to the best German fighters. Luftwaffe losses climbed to unsustainable levels. Experienced pilots died faster than replacement pilots could be trained. By mid-1944, the Luftwaffe had effectively lost air superiority over Germany. American bombers attacked targets with decreasing interference. The Norden bombsights that German engineers had examined so carefully in 1943 continued doing their work, guiding bombs onto refineries, aircraft factories, ball-bearing plants, and marshalling yards. The cumulative destruction crippled German war production. The examination of captured American equipment continued even as Germany's situation deteriorated. Each new device revealed similar patterns. American equipment showed consistent quality, sophisticated engineering, and manufacturing precision that German industry struggled to match. Proximity-fused anti-aircraft shells captured in early 1945 showed miniaturization of radio electronics that German engineers had declared impossible. Captured M1 Garand rifles demonstrated automated production of precision firearms at scales that exceeded German rifle production by factors of 10. Sherman tanks, dismissed by German propaganda as inferior, revealed thoughtful engineering focused on reliability and ease of production rather than maximum performance. Every examination reached the same conclusion. America had organized its industry for mass production of adequate equipment, while Germany had organized for small-scale production of superior equipment. In a war of attrition, America's approach was proving decisively superior. The captured Norden bombsights were eventually destroyed as Allied forces advanced into Germany. Some were demolished by retreating German forces to prevent recapture. Others were lost in the rubble of bombed facilities. The technical reports, filed in archives in Berlin and other locations, were captured by Allied forces in the final weeks of the war. American intelligence officers read the German assessments with considerable interest. The reports confirmed what American planners had understood. The Norden bombsight represented not just technical sophistication, but industrial capability that America's enemies could not match. Post-war analysis of the strategic bombing campaign revealed that the Norden bombsight's actual combat effectiveness fell short of the extraordinary accuracy demonstrated during peacetime tests. Combat conditions, weather, fighter attacks, anti-aircraft fire, crew stress, and simple human error degraded accuracy significantly. Studies indicated that under combat conditions, only about 20% of bombs dropped fell within 1,000 feet of the aim point. This was still far better than unguided bombing, but it was not the precision that propaganda had suggested. Yet, the Norden sight had achieved its strategic purpose. German engineers and officers who examined captured examples understood that they faced an enemy with industrial resources that exceeded Germany's capacity to counter. The Bombsight became evidence of American industrial sophistication, and that evidence contributed to the growing realization among German leadership that the war was lost. The psychological impact matched the material impact. Every examination of captured American equipment reinforced the same message: German industry could not match American production in quantity or quality. This understanding spread through technical communities, military staff organizations, and eventually to senior leadership. By early 1945, even the most committed Nazi officials privately acknowledged that Germany faced inevitable defeat. The industrial disparity was too great to overcome through willpower or tactical innovation. For the engineers who had spent months examining the Norden bombsight, this realization came early. They had measured the precision, documented the sophistication, and calculated the impossibility of matching American production. They understood that every bombing mission over Germany involved dozens of these complex devices, each representing manufacturing capabilities that Germany did not possess. They knew that American factories were producing replacement bombsights faster than the Luftwaffe could shoot down the bombers carrying them. This knowledge, shared through technical reports and personal discussions, contributed to the collapse of confidence that preceded Germany's military collapse. The Norden bombsight, intended as a secret weapon to enable precision bombing, had served an additional purpose. It had demonstrated American industrial power to Germany's most knowledgeable technical experts. Those experts, examining the captured devices with professional respect for the engineering and manufacturing skill they represented, reached conclusions that propaganda could not counter. America's industrial capabilities exceeded Germany's by margins that made defeat inevitable. The technical intelligence gathered from examining Norden bombsights was distributed through German military and industrial channels, with increasing urgency as the war progressed. By late 1944, copies of the detailed reports reached aircraft manufacturers, optical companies, precision instrument makers, and military research facilities across Germany. The response from German industry proved revealing and deeply troubling. Engineers at Carl Zeiss acknowledged that while they could produce optical components matching the Norden sight's quality, they could do so only in small quantities using highly skilled workers and lengthy production times. Scaling up to produce hundreds per month, much less thousands, would require machine tools and automated grinding equipment that did not exist in Germany and could not be built within any relevant time frame. Siemens engineers examining the mechanical computing components reported similar conclusions. The differential gears and cams could be manufactured in Germany, but only as prototype or small batch production. The precision required meant that each component needed individual inspection and often hand-fitting by master machinists. American production methods apparently eliminated hand-fitting through sufficiently precise automated machining that parts were interchangeable without adjustment. This represented a fundamentally different approach to manufacturing. German precision equipment relied on skilled workers to achieve final precision through careful fitting and adjustment. American precision equipment achieved its precision through machine tools, capable of producing components that required no fitting. The American approach required massive investment in tooling, but enabled rapid production by less skilled workers. The German approach required less tooling investment, but demanded skilled craftsmen who were in critically short supply. The gyroscope assemblies presented perhaps the most daunting manufacturing challenge. The rotor had to be perfectly balanced, spinning in bearings with virtually no friction, mounted in gimbals that allowed free movement in all axes while maintaining precise alignment. German companies produced similar gyroscopes for aircraft instruments and naval fire control systems, but production rates measured dozens per month, not thousands. When German engineers calculated the resources required to match American Norden bombsight production, the numbers proved devastating. Establishing production capacity for 1,000 bombsights per month would require diverting machine tool production equivalent to what was needed for 200 fighter aircraft. It would require recruiting and training 5,000 skilled workers at a time when skilled labor was already desperately short. It would require precision grinding equipment, optical manufacturing capacity, and quality control systems that would take years to establish. Most critically, it would require raw materials, high-grade optical glass, precision-bearing steel, aluminum alloys that Germany was struggling to obtain in sufficient quantities for existing programs. The conclusion was inescapable. Germany could not produce Norden bombsights in militarily significant quantities, even if detailed manufacturing plans were available. The industrial infrastructure simply did not exist and could not be created quickly enough to matter. This realization extended beyond the specific case of the bombsight. German engineers examining captured American equipment throughout 1944 and 45 repeatedly encountered the same pattern. American equipment showed consistent quality, sophisticated engineering, and most significantly, evidence of mass production systems that German industry had not matched. The M4 Sherman tank, examined extensively after hundreds were captured or knocked out in Normandy, revealed similar patterns. German engineers initially dismissed the Sherman as inferior to German tanks like the Panther or Tiger. The Sherman's 75mm gun could not penetrate German heavy tank armor from the front. Its armor was thinner than German tanks. In a one-on-one engagement, German tanks appeared superior. But detailed examination of captured Shermans revealed aspects that German engineers found deeply troubling. Every component showed evidence of automated production. Castings were precise and consistent. Welding was uniform across all examples examined. Electrical systems used standardized components and color-coded wiring that made field maintenance simple. The engine, a modified commercial design, could be removed and replaced in hours rather than days. Most significantly, Shermans showed complete interchangeability of parts. A transmission from one Sherman would fit any other Sherman of the same model without adjustment. Final drive assemblies, suspension components, track links, all were precisely manufactured to specifications that made them interchangeable. This meant that damaged Shermans could be repaired quickly using parts from other damaged vehicles. It meant that supply systems could stock replacement components, knowing they would fit any tank in the field. German tanks, by contrast, required skilled mechanics who could adjust and fit components to individual vehicles. Parts from one Panther would often require modification before fitting another Panther. Field repairs took longer and required more skilled personnel. The German approach produced tanks with arguably superior combat performance in individual engagements. The American approach produced tanks that could be manufactured rapidly, maintained easily, and kept operational under field conditions. In a war of attrition, the American approach was proving superior. By late 1944, Germany was losing tanks faster than factories could replace them, while American tank production exceeded losses by wide margins. The examination of captured American field equipment revealed similar patterns everywhere. American field radios used vacuum tubes that could be replaced like light bulbs. German radios required skilled technicians to adjust and tune replacement tubes. American artillery pieces showed interchangeable parts and simple maintenance procedures. German artillery required more specialized maintenance. American small arms, the M1 Garand rifle, the M1 carbine, the Browning automatic rifle, all showed evidence of automated production using stamped parts and simplified designs that enabled rapid manufacturing. German small arms remained predominantly milled from solid steel, requiring extensive machining time. The cumulative evidence from examining captured equipment led thoughtful German officers and engineers to a profound realization. Germany had been fighting the wrong kind of war. German industry had been organized to produce sophisticated equipment in limited quantities, relying on skilled craftsmen and accepting long production times. American industry had been organized to produce adequate equipment in overwhelming quantities, relying on automated production and accepting the massive upfront investment in tooling. For a short war decided by tactical brilliance and initial equipment superiority, the German approach might have succeeded. For a long war of industrial attrition, the American approach was proving decisively superior. This understanding spread through the German technical community during the final year of the war. Engineers who had examined captured equipment shared their conclusions with colleagues. Technical reports circulated through military and industrial channels. By early 1945, the realization that Germany had been outproduced by margins that made ultimate defeat inevitable had become widespread among those with access to classified intelligence. The propaganda that filled German newspapers and radio broadcasts spoke of wonder weapons that would turn the tide. V-2 rockets, jet aircraft, new U-boats. Engineers who had examined American equipment understood these wonder weapons would come too late and in too few numbers. Germany had invested in sophisticated weapons that required advanced technology and scarce resources. America had invested in production systems that could manufacture adequate weapons by the millions. The Norden bombsight examinations continued even into the final weeks of the war. A B-17 shot down near Munich in March 1945 yielded another intact bombsight. Engineers at the facility examining it noted that the device showed the same precision and quality as examples captured 2 years earlier. There was no evidence of declining quality or simplified production. American industry was maintaining its precision manufacturing standards, even as production volumes increased. This consistency reinforced the most demoralizing conclusion. American industrial capability was not straining to meet demand. The equipment arriving over Germany in increasing quantities represented only a fraction of American industrial capacity. The examination reports from March 1945 carried an undertone of resignation absent from earlier reports. Engineers documented technical details professionally, but their conclusions acknowledged that the information had no practical value. Germany lacked the time, resources, and industrial infrastructure to apply any lessons learned. The strategic bombing campaign, guided in part by those Norden bombsights that German engineers had examined so carefully, had systematically destroyed Germany's remaining industrial capacity. Aircraft factories, ball-bearing plants, synthetic fuel refineries, and transportation networks all suffered catastrophic damage. By April 1945, German war production had collapsed to a fraction of peak output. Remaining factories operated sporadically, limited by shortages of raw materials, electrical power, and transportation. As Allied forces advanced into Germany from east and west, the facilities where captured American equipment had been examined fell into Allied hands. American technical intelligence teams found the German reports with considerable interest. The detailed documentation of Norden bombsight components confirmed that German engineers had thoroughly understood the device's operating principles. What the reports also revealed was that German engineers had recognized their inability to match American production. American intelligence officers reading the reports noted the tone of professional respect mixed with resignation. German engineers had accurately assessed American industrial capabilities and correctly concluded that Germany could not compete. The psychological impact of this realization, spread through German technical and military communities, had contributed to the collapse of German will to resist in the final months of the war. After Germany's surrender in May 1945, American investigators conducted extensive interviews with German engineers, military officers, and industrial leaders. Many mentioned the examination of captured American equipment as a turning point in their understanding of the war's likely outcome. A former Luftwaffe technical officer interviewed in July 1945 described the impact of examining a captured Norden bombsight in early 1944. "We understood immediately that we were looking at something our industry could not produce in quantity," he stated. "The precision was extraordinary, yes, but what struck us most was the evidence of mass production. Every gear, every bearing, every component showed machining quality that we associated with prototype equipment or laboratory instruments. Yet intelligence reports indicated thousands of these devices had been built. This meant American industry possessed capabilities we had not imagined," he continued. When you realize your enemy can produce complex precision equipment in quantities that exceed your total production of all equipment types combined, you begin to understand the war is lost. It becomes a question not of if, but when. The Bombsight examination made this clear to many of us who worked in technical fields. We shared this understanding with colleagues, and it spread. By late 1944, most engineers I knew privately acknowledged defeat was inevitable. The only question was how much more destruction Germany would suffer before the end came. Similar sentiments appeared in numerous interviews conducted during the immediate post-war period. German officers and engineers who had examined captured American equipment consistently described a progression from initial technical interest to growing concern as they recognized the sophistication, to final resignation as they calculated the impossibility of matching American production. The United States Strategic Bombing Survey, conducted immediately after the war, included extensive analysis of German technical intelligence activities. The survey team found that German examination of captured equipment had been thorough and professional. German engineers had accurately assessed American capabilities in most cases. Where German assessments proved inaccurate, they typically underestimated rather than overestimated American advantages. The survey concluded that German technical intelligence had provided accurate information to German leadership about relative industrial capabilities. The problem was not lack of intelligence, but inability to act effectively on that intelligence. Knowing that American industry could outproduce German industry by factors of 5 or 10 did not change the fundamental equation. Germany could not significantly increase production without resources and industrial infrastructure it did not possess. The Norden bombsight became, in post-war analysis, a case study in the importance of industrial capacity in modern warfare. The device itself was sophisticated and effective within its design parameters, but its true significance lay not in its technical specifications, but in what it revealed about American industrial organization. The ability to mass-produce precision instruments demonstrated capabilities that Germany's enemies had not anticipated. Post-war examination of American production records confirmed what German engineers had suspected. At peak production, American factories were manufacturing more than 1,000 Norden bombsights per month. Total production exceeded 50,000 units by the war's end. This represented an investment exceeding $1.5 billion in 1940s currency, more than the entire German military research and development budget for selected years. The infrastructure supporting this production was equally impressive. More than 200 companies participated in manufacturing components. Specialized machine tools were developed specifically for producing bombsight parts. Training programs taught thousands of workers to assemble and test the complex devices. Quality control systems ensured consistent precision across all production facilities. This industrial mobilization represented capabilities unique to the United States. No other nation possessed the combination of machine tool industry, skilled workforce, raw material access, and capital availability necessary to undertake such programs. Britain, despite superior scientific research in many fields, lacked the industrial capacity for this scale of precision manufacturing. The Soviet Union possessed large-scale industrial capacity but lacked the precision manufacturing infrastructure. Germany had precision manufacturing capability but could not achieve the necessary production volumes. Only America could combine precision with mass production at the scale required. The lessons German engineers learned from examining the Norden bombsight extended far beyond the specific device. They had discovered that modern industrial warfare required not just technical sophistication, but also systematic organization of production, massive investment in tooling and infrastructure, and acceptance of high initial costs in exchange for eventual high-volume output. These lessons influenced post-war German industrial development. Engineers who had examined American equipment during the war brought that knowledge to Germany's reconstruction. The Federal Republic of Germany's economic miracle of the 1950s and 60s drew partly on understanding of American production methods gained through wartime technical intelligence. German companies that adopted American-style mass production techniques, Volkswagen's adoption of assembly line methods, Siemens's investment in automated manufacturing, achieved success in global markets. The irony was profound. Technology that Germany had examined as an enemy during the war became a model for German industrial recovery afterward. Engineers who had written reports analyzing why Germany could not match American production applied those same analyses to reorganizing German industry along more efficient lines. The Norden bombsight itself continued in American service through the early years of the Cold War. Improved versions equipped B-29 superfortresses during the Korean War. The last combat use occurred in the early 1950s. By then, radar bombing systems and early computer-guided weapons were making optical bombsights obsolete. The sophisticated mechanical computer that had so impressed German engineers in 1943 was being replaced by electronic systems that offered even greater capability. The machine tools and production techniques developed for Norden bombsight manufacture found new applications. Precision manufacturing methods pioneered for the bombsight influenced post-war electronics production. Workers trained to assemble complex mechanical instruments transitioned to assembling early computers and electronic equipment. The industrial infrastructure created for wartime production became the foundation for America's post-war technological leadership. Carl Norden, the engineer whose design had so impressed German technical experts, continued working on precision instruments after the war. He died in 1965, having lived to see his bombsight become obsolete, but his manufacturing techniques become standard throughout precision industries. His insistence on extreme precision and his collaboration with American mass production expertise had created a device that served its tactical purpose while demonstrating America's industrial superiority. The German engineers who had examined Norden bombsights in Berlin during the war faced different fates. Some died in the final months of combat. Others were captured and interrogated by Allied technical intelligence teams. Several were recruited to work on American or Soviet military programs during the Cold War, bringing their expertise in precision instruments to new applications. Those who remained in Germany and contributed to post-war reconstruction often spoke of the examination of American equipment as a formative experience. They had seen firsthand what systematic industrial organization could achieve. They had measured the precision and calculated the impossibility of matching it with existing German methods. They had learned that success in modern manufacturing required not just skilled craftsmen, but systematic processes, automated production, and massive investment in tooling. These lessons, learned through the careful examination of a captured bombsight, helped shape the industrial policies that rebuilt German manufacturing in the post-war era. The story of the Norden bombsight examination reveals a paradox at the heart of World War II. Germany entered the war with arguably the world's most sophisticated engineering community and a well-deserved reputation for precision manufacturing. Yet Germany lost an industrial war to nations whose engineers German propaganda had dismissed as inferior. The resolution of this paradox lay not in individual technical skill, but in systematic industrial organization. German engineers could design and build extraordinarily sophisticated equipment. What German industry could not do was produce sophisticated equipment rapidly in quantities that would overwhelm enemy defenses through numerical superiority. American industry had solved exactly that problem. The Norden bombsight demonstrated the solution. Invest heavily in precision tooling, design for manufacturability, establish quality control systems that built precision into the process rather than relying on skilled adjustment, and accept that initial costs would be high, but eventual unit costs would fall dramatically as production volumes increased. For every Norden bombsight examined by German engineers, hundreds more were being installed in American bombers. For every detailed technical report filed in Berlin, dozens of B-17 seconds and B-24 seconds were rolling off American assembly lines. The disparity was not in engineering skill but in industrial capacity and systematic organization. By the final months of the war, German engineers examining captured American equipment were no longer looking for technical insights that might be applied to German production. They were documenting the evidence of their own defeat, measuring the precision they could not match, calculating the production volumes they could not achieve, and recognizing that they had been fighting an enemy whose industrial capabilities exceeded Germany's by margins that made ultimate defeat inevitable. The Norden bombsight that Oberleutnant Richter had extracted from the wreckage in that snow-covered field in March 1943 had told its story. German engineers had listened, measured, calculated, and understood. They had recognized that they were examining not just a bombsight, but a demonstration of industrial superiority they could not counter. That recognition spread through German technical communities, military staff organizations, and eventually senior leadership. It contributed to the collapse of confidence that preceded military collapse. It demonstrated that propaganda claims of German technical superiority were false, and that American industrial power was real and overwhelming. The device that had been developed in Brooklyn workshops by a difficult but brilliant engineer, manufactured by the thousands in factories across America, and deployed in bombers attacking Germany from bases in England, had served its purpose. It had guided bombs to targets, yes. But perhaps more importantly, it had demonstrated to Germany's most knowledgeable engineers that they were fighting an unwinnable war. The precision machined into every gear and cam, the sophisticated optical systems, the gyroscopic stabilization, all represented capabilities that German industry could not match at the required scale. Every examination confirmed the same conclusion. Every technical report reached the same verdict. Every calculation produced the same result. American industrial superiority was overwhelming and decisive. In the end, the Norden bombsight achieved its strategic purpose, not through the accuracy of the bombs it guided, but through the message it delivered to those who examined it. Germany had entered an industrial war against an opponent whose capabilities exceeded German understanding. The sophisticated mechanical computer that calculated bomb trajectories also calculated the trajectory of the war itself, and the calculation was clear. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.